In this video, we're going to compare the concept of work and power. So we want to ask the question, what is the scientific definition of work? And this person on the left pushing on this car, is this man doing work based on that definition? And if so, how much? We also want to ask the question, what's the difference between work and power? And this weightlifter lifting these weights, how much power is this person exerting on these weights in a certain amount of time? So we're going to start with the definition of work. So work is the transfer of energy to or from an object when a force acts on it over a distance. So we can use this circle to represent the energy in our system. And we can think of work as the mechanism that transfers energy in or out of our system. The equation, the way we calculate work, is force times displacement if the force and the displacement are parallel to each other. So if they are not, then we have to take into account the angle. So work is force times the displacement cosine theta. So the cosine theta is needed if the force and the displacement are not parallel to each other. We'll look at that in a moment. We're going to first look at situations where they are parallel to each other. But we also want to make a note of the units. The unit for work is a joule. The unit for force is newtons. The unit for distance is meters. So 1 joule is equal to 1 Newton meter. So once again, this is assuming that the force and the displacement are parallel to each other. And if they're not, then we need to take into account their angle. Now we're going to look at some examples. We'll start with what we call positive work. And this occurs when the force is moving is in the same direction as its displacement. So this box is pulled to the right, and it's also moving to the right, so we will get a positive work. Negative work occurs when the force is in the opposite direction of the motion of the object. So the object is moving to the right, and maybe perhaps this is a bumpy surface, and so there is some friction in the opposite direction. Even though the object is moving to the right, the force is to the left. And so in this situation, we would get what's called negative work. So negative, this tells us, in this case, that the force and the displacement are in opposite direction. And then finally, we have a object. Let's say that here is a wall right here. We've got a wall right here, and you're trying to push this box over here to the right. Okay, so although you have a force, so there is a force, you're pushing it to the right. Okay, because this box is not moving, the displacement is 0, so your work is going to be 0. So in our first situation, we're going to have what's called positive work. Okay, you're going to get two numbers, you multiply them, and you get a positive number. And then negative work occurs when your force and your displacement are in opposite direction. And 0 work is going to equal 0 if the object is not moving. So when we say that work is positive, what do we mean? So going back to our circle with the energy in our system representation, what we're saying is that if the work is positive, we're transferring energy into our system. And so in this case, assuming a frictionless surface, if you apply a force on this block over certain amount of displacement, the speed of this block will increase. And later on, we'll learn something about kinetic energy, the energy of motion. And we'll see that this block actually has an increase in kinetic energy. Now, what do we mean about negative work? So negative work, once again, using our system representation here and energy of our system, what's going on here is that work is moving energy out of our system. So energy is moving out of our system. In this case, this block on this friction surface, this rough surface, is going to slow down. And so the kinetic energy of this block is going to decrease. And then what do we mean that the work is 0? So what that means is that the energy is not going in or out of the system. And so the total energy in our system remains the same. Now let's take a look at examples of this vertically. So vertically, you can have a ball that's falling, and perhaps the gravitational force causing it to fall. And since it's pulled in the direction that it's moving down. This would be an example of positive work. Okay. Now we have an example where you throw the ball up. So you throw the ball up, so the velocity is upward, but the force of gravity is still downward, right? So this would be negative work, okay? In this case right here, even though it's being pulled down by gravity, Fg, the work, since it's not moving, since the distance is 0, d equals 0, the work equals 0. So here we're talking about the work done by gravity pulling down. Now there's also work done by the hand pushing it up. And that work is also 0 since it's not moving. The work done by the hand is going to be 0. So when we think about work, there could be work done by different forces. In this case, we have work done by the gravity force. We also have work done by the normal force from the hand pushing it up. So once again, I want to go over what we mean by positive work. So here's my circle representing the energy in my system. If we have positive work, that means we have energy going into the system. In this case, this ball is going to go faster and faster. Let's say in this situation, we have the ball is going up and the force is going down. We have a negative work. In this case, the energy is leaving our system. In this case, specifically, we're dealing with kinetic energy, the energy of motion. It's going to be going slower. And finally, if the work on our system is 0, then there's no energy going in or out. Now, in this case, we do have a force upward, we do have a force downward, but the net force is 0. The net force is 0, and it's also not moving, so the energy in our system remains constant. Now we're going to take a look at forces at an angle. What happens if the force is not parallel to the direction of the object's motion, but at an angle? So here we have a force at an angle of theta. It's moving to the right, displacement d. So the equation we use is work is equal to force times the displacement cosine theta. Okay, so we need to take the angle into consideration. So let's take a look at some examples. So if the forces, the force and the displacement are in the same direction, theta is going to be 0, and we're going to get positive work. So we saw that earlier. If the force and the displacement are in opposite direction, then theta will be 180 degrees, and we get negative work. And we saw this earlier as well. But if the force is at an angle, let's say that it's at an angle of 45 degrees, so let's say theta is 45 degrees, then we would have to calculate the force times the displacement and times cosine 45. So we would write in cosine 45 to calculate the work. If the force, take a look at one more example. If the force and the displacement are 90 degrees, so this is an interesting situation. So if it's 90 degrees, then cosine 90 degrees is going to be 0. So the work is going to be 0. So this is interesting because we saw that work is 0 if the displacement is 0. The work is also 0 if the force is 90 degrees or perpendicular to the displacement. Now let's work through some calculations. All right, so in our first problem, we have a force to the right of 3 newtons. We have a displacement of 2 meters. So the work is going to be 3 times 2. And since the angle is 0, cosine 0, cosine 0, and cosine 0 is just 1, so it's just going to be 6 joules. Now, if the force is in the opposite direction of the displacement, and let's say the force here is 3 newtons, displacement is 2 meters, the work is going to be 3 times 2, and now it's going to be cosine 180 degrees, and cosine 180 degrees is -1, so we end up with -6 joules. All right, so now let's take a look at a problem where we have a angle, and our angle here is 45 degrees. We have a force of 3 newtons. Our displacement is 2 meters. And we're going to calculate the work, which is going to be the force 3 times 2. The displacement is 2 cosine 45. So here's where the cosine comes in. And it's going to be 6 times cosine 45, which we get 4.2 joules. Okay. So notice that 4.2 joules is less than 6 joules. So another way to think about this cosine 45 is to think of the component, the parallel component right here, this component right here. So what it's doing, what this cosine 45 is doing is it's getting you the component of the force that is parallel to the displacement. And so that's just another way. So 3 cosine 45 will give you this component. Remember, this is a force at an angle, so it's made up of 2 components. And this 3 cosine 45 is giving you this parallel component to the displacement. All right, so we'll look at one more problem here. Let's say that we have a displacement of 2 meters, once again, to the right. So d equals 2 meters to the right. But this time we have a force upward. So force of 3 newtons, okay? So what if we have a force up and we have a displacement of 2 meters, what's the amount of work? So the work here is 3 times 2 cosine 90 degrees. Okay, so 6 times cosine 90 is 0, so anything times 0 is 0. So this force upward is not doing any work on this box here. So this box here moving towards the right, and kind of makes sense because we know that an object, assuming there's no friction here or air resistance, we know that an object at rest will continue to stay at rest, and there's an unbalanced force. So once this is moving, it's going to keep on moving. There's no force required horizontally to keep it moving. So now we want to ask the question, how much work is this man doing in this problem? If he's pushing with a force of 400 newtons and pushes it over a displacement of 8 meters, so it's pushing it a distance of 8 meters, we know that work is FD cosine theta. So the force is 400, the distance is 8 meters, and then cosine, since it's in the same direction, it's going to be cosine 0, and that's going to be 3,200 joules. Now let's take a look at the definition of power. So power is the rate at which work is done. When you see this word rate, we're thinking about something to deal with time. So in this case, how quickly work is getting done. And so the equation for power is work divided by time. And the unit for power is watt. The unit for work is joules, and the unit for time is seconds. Now, this unit of watts is interesting. You may have noticed that when you purchase a light bulb, and the reason you see that labeled is because it's telling us how quickly energy is getting transformed. So another way of thinking power is how quickly energy is being transferred or transformed. And in the case of a light bulb, the electrical energy is transformed into light energy. So how quickly that's occurring is what we refer to as the power, and the unit for power is watts. Now let's take a look at a couple power questions. A motor exerts a constant force of 300 newtons to lift an object 10 meters vertically in 5 seconds. So what is the motor's power output? So power is work divided by the time. And we know work is force times the displacement cosine theta divided by t. Okay, so the force here is 300 newtons. The displacement is 10, and we're assuming that the force and the displacement are in the same direction. So cosine 0 is just going to be 1, and the time is 5 seconds. So we have 300 times 10, 3,000 divided by 5, and we get 600 watts. Now let's take a look at a second power question. A cyclist is riding at a constant velocity of 10 meters per second while experiencing a total resistive force from air resistance and friction of 200 newtons. What is the cyclist's power output needed to maintain this velocity? Now what's interesting about this question is it doesn't tell you the displacement, so we're going to have to manipulate the power equation a little bit. Power is work divided by the time, and work is force times displacement. Cosine theta, I'm going to assume that the force and displacement are in the same direction, divided by the time. Now we know from kinematics that displacement divided by the time is velocity, so we can rewrite this as force times the velocity. We know the force, 200. We know the velocity is 10, so the power is going to be 2,000 watts. Now let's take a look at this weightlifter and answer the question, how much power is exerted by this weightlifter? So let's just say that the weights are 300 pounds, which is about 136 kilograms. This weightlifter does a front squat, which pushes the weight up a displacement of 0.7 meters, and it takes him 2 seconds to lift these weights up. So we're going to use, once again, our power equation. Power is equal to work divided by the time. So the work is force times displacement, cosine theta, but it's in the force in the same direction as the displacement, divided by the time t. And the force is, we need to calculate this into weights, because right now this is actually the mass. So to get the weight, it's going to be mgd. That's going to give us the weight divided by t. Okay, so m is 136. The g is 9.8. Displacement is 0.7. And then the time is 2 seconds. And we calculate all that, we get 467 watts.